Okay, I'll start recording for a bit and then I'll pause because we're gonna do some group stuff. Thank you for being here. Happy Tuesday. I have some announcements for you. One of which is there's a retreat that's happening this weekend, hosted by the Mission and Ministry Center. This is it. Finding your north, which is about like aligning your figuring out like what your vocation is and what your aspirations are. I was on retreats like this when I was a student, and I always found them to be helpful and refreshing. So if you're free this weekend, consider this. Registration is $45, but there's financial assistance. And if you have questions, you can contact Nate or Eddie, and I can forward these emails to you if you want. The other announcement is, oh, we've got a note. Yeah. So the other announcement is there's a book scholarship that's available. Again, if you're a senior, this maybe doesn't apply to you, but if you're not a senior, there's a book scholarship where you get up to $250 to buy your textbooks. I received this scholarship as a student and it was extremely helpful. I think the rule is that you can only get it one semester a year, so either fall or spring. So to find out more, it's put on by the Intercultural Center. So if you Google St. Mary's Intercultural Center book scholarship, chances are it'll lead you there. Again, or I can send you along the information. Okay. Minimize. Those are my announcements. For reminders, so most things have been graded except for the video. I'm hoping to get in at like 8 a.m. tomorrow morning and grade the video. So everything else has been graded apart from the homework that's due today. So take a look at your grade. Ask me if you've got any questions or need some clarifications. I tried to put most of the explanation in Canvas. So some of you, if you have paper homework, I think I tended to put the explanations in Canvas. So just let me know if you have questions on how I graded a particular problem. The homework for divide and conquer is due tonight. Make sure you get that in. I can take paper copies if you have them. Just a reminder to like snap a picture of it before you turn it in, just in case anything happens. And before you leave, I would like your divide and conquer packets as well. All right, any questions before we get started? Okay, so we're gonna start a new unit. So you've got the packets, and the new unit is graph algorithms. This is one that we're gonna have a video for again. I'm thinking to have it due. Let's see if we can view the calendar for this class. So here's where we are right now on the 18th. The week of the 31st is spring breaks. It's spring break. And so I'm thinking the graph algorithms video might be due on this Thursday or Friday. That's tentative because we're planning to have an exam on the Thursday. I'm gonna think about it a little bit more, but what I'm gonna do today is try and make the groups. So I'm gonna pause recording, and because the idea for the video, go up to the top. Can I go up to the top? So we're going to cover some algorithms, and you're going to do the similar process for the video for these algorithms. And I want to break you into groups where, like, if you were the videographer this time, you shouldn't be the videographer this time. So I'm going to pull up a spreadsheet and try and get a list of who was what. And then maybe this class or next class, I'll come back with here are all your groups. All right, so in terms of the actual video assignment, it's pretty much the same. It's just instead of being assigned a data structure, you're going to be assigned a graph algorithm. Again, it's hopefully less than or equal to 5 minutes. And the deliverables are roughly the same. So except for the architect, I would like you to come up with 2 examples and then choose the best one just to try and help cut down on time. Again, once I go through and grade the first one, then you'll have a better idea. I'll have a better idea of maybe common mistakes or how to cut down. For the programmer, this is going to be in 2 parts and is probably going to be slightly easier than the previous one. So that's why I'm thinking about making it due before spring break, because I think it shouldn't take as much time to implement. So the architect gives the programmer an example, and the programmer, one of the simple examples, and the programmer will implement that without using a library. So just using like built-in code data structures. We'll talk about this in a bit. And then coming up with some non-trivial example and install a graph library and use that library to analyze things. Again, we'll go over this once we've talked about graphs and all that stuff. So I think the programmer task is slightly easier this time. Then the videographer is, I have to revise that. The videographer role is also roughly the same. Okay. The other thing I'll note is that we're going to go over these 5 algorithms in class. If you talk with your group and you want to try to learn a new algorithm, please do so. Just let me know which one, and I'll approve that. Okay, so that's the video. Let's talk about graphs. All right, so we're in a new module on Canvas, and you should hopefully have and I'll go back to the page. The packet's also on Canvas, as usual. Okay, so for this one, I've merged together 2 of the chapters in the textbook, chapters 7 and 8. 7 looks at just like graph algorithms in general, and then 8 looks at weighted graph algorithms. So I've combined them. And the motivation for this is, who here has ridden like Muni in the city? Yeah, so you'll know there's a difference between looking at something like the map on the right, which it's got like parks and streets, and in addition to it's got the colored lines that represent the trains. And there's a difference between that one and the one on the left, which is a more, I don't know, less representative version of here's the stops and the train lines. Also, if you go on the train, I need to go and ride it so that I can take a picture of it. But you know how when you're on the train and like up above the door or something, there's like the rectangle version of the map where it's even like it's taken all of these and lined them up just into straight lines. This is what we're looking at when we talk about graphs. Remember at the very beginning, we talked about abstraction. So we are abstracting the information of here's where the spots, the train stops are, and we've extracted only the relevant information, and we're storing them as a graph. Okay, I forgot to finish this outline. But we're going to talk about what is a graph. We're going to talk about how we can represent it. And then we're going to talk about some algorithms, which include traversals and some for weighted graph algorithms. Oh, wait, no, I did finish the outline. So yeah, so we're going to look at traversal algorithms like breadth first search and depth first search, and then weighted ones. So this is also a graph. It's a collection of nodes and edges where the nodes are the dots and the edges are the lines between the dots. And we can have weights on them if we want. So like from Las Vegas to Salt Lake City, there's a weight of 12. What that weight is depends on what sort of information we want to track. I have a symbol graph for the book has one for Harry Potter. I like Spider-Man, and so I was like, let's make a friendship graph for Spider-Man. Where in the second video game, Peter Parker is friends with Miles Morales and Mary Jane Watson, and both Peter and MJ are friends with Harry Osborn. Harry is friends with his dad, Norman. Peter Parker is also friends with a police captain. And so we can draw a graph that says, like, X is friends with Y. And so each person gets their own node, their own vertex, and friendship is an edge between them. So there's different questions we can ask given a graph like this. One of the questions is, if I am friends with you, does that automatically imply that you are friends with me? And so what that gives us is the notion of, is the graph directed or undirected? Which, if you're in 485, we've talked about this a lot today. So an undirected graph is just this, where we have vertices and edges. A directed graph is when we add an arrow to it. So this is saying X is friends with Y, but Y is not friends with X. We can't go the other way when there's an arrow. If there's no arrow, then this means that if X is friends with Y, Y is also friends with X. So it goes both ways. We can also have a measure of how close of friends are X and Y. So maybe if they're BFFs, then they get a weight of 10. But if they just met each other once in a coffee shop, then they maybe have weight of 1. Yeah. Mm-hmm.
That's like X from Y, Y.
Yeah. Yeah, they're both friends with each other. The other question is, could I be friends with myself? And the way that we represent this in graph is with what we call a loop. And this is where we get into the definition of a simple graph, which is, this is just like very broadly talking about different graph definitions. If we have an undirected graph and we have something like X and Y and there's 2 edges between them, what does that mean in terms of friendship? I'm not really sure. But the notion of a simple graph is something that doesn't have this loop or this multiple edge. So that's simple graphs. For degree, we can ask who has the most friends. So, okay, I'm going to go back to the previous slide. So for this question, who has the most friends in this graph? What do you think? Peter Parker, right? So this is the notion of degree, of how many edges are associated with each vertex. So Peter Parker has 4 friends, whereas MJ only has 3, and so does Harry, and then Miles and Yuri have less, at least in this graph. So Peter Parker would be the person with the most friends, and we represent this number of edges. That's what we call the degree. So the degree of Peter Parker is 4. Okay, more questions. Do they live close by? This is something that the book calls an embedded graph. I don't know that I've ever seen it in the wild, but I want to mention that it's possible, which is where you take some of this information and you embed it in the plane so that maybe like person X lives at this spot and then 2 miles away, person Y lives at this spot, and you can get there by following a path that's 2 miles long. So embedding this information in like a location. Then we can say something of along the lines of, oh, you know them too. So maybe X knows Y, who knows Z, and maybe X also knows Z. If one of the things we like to bring up for this one is the Erdős number, which is was a prolific mathematician who wrote many papers with many people. And so there's this notion that if you publish a paper with someone who has published with the original guy, then you get an Erdős number. So I've published a paper with my PhD advisor, who published a paper with a co-author of Erdős. And so I would have an Erdős number of 1, 2, 3. There's also, has anybody heard of the Kevin Bacon number? Yeah, so this is also the same kind of idea where if you have an acting credit, how many degrees of separation do you have from being in a film with Kevin Bacon? And then there's the idea of the 6 degrees of separation, which is the hypothesis that every person is at least 6 degrees away, or like 6 people from knowing another person. So that's a fun thing. Another question is, are you an individual? Like, do you have a name, or are you just part of a crowd? Okay, so those are the kind of like, that's my speed through. Here are the graph definitions. Now we're going to talk about what data structures we use. So the thing to remember here is that a graph is a set of, it's got 2 things associated with it. It's got vertices, which are nodes, and edges. And so vertices, those are the dots, and then edges are the things connecting them. So pretty much anything can be described, a lot of things can be described as a graph. You just have to define what are the vertices and what do the edges mean? What's the relationship between them? How can we say that this constitutes a graph? If you can say those 2 things of what are the vertices and what do the edges mean, then you've got yourself a graph. Then you can do graph algorithms. So we'll talk about this at a relatively high level, but there's a ton of ways you can apply this. Okay, so I would like us to talk for a moment. So there are some answers that I'm gonna walk through, but I want you to talk among your neighbors for a second, and then I'll elicit ideas of how should we represent a graph, like in terms of data structure, or how do we do this in code? So talk about it with your neighbors for a second. All right, what do you think? How should we represent a graph? How should we store this information? What are your ideas? Yeah.
First thing we're talking about is like a tree just comes to mind, just the same kind of structure.
Yeah.
It's
Mm-hmm. Yeah, so I will note that a tree is a kind of graph. So a tree is a special kind of graph. In graphs, there's a notion of something called a cycle, which is something that we can, like if we start at one vertex and go all the way around, we get back to the vertex that we started at. A tree is what we call an acyclic graph, or something without cycles. So a tree is a special kind of graph. But there are ways that we represent a tree in a program, like maybe we use an array. Yeah, what were you thinking in terms of linked list?
just like if you have some nodes that have or are connected or related to
Mhm.
one node to the next. But I don't think one.
Like that. Yeah, so that's a good idea. So this is definitely possible. You can actually have like something like this, where one node points to multiple nodes. You just have to adjust your data structure. So if you define your node class, typically you have like some data and then maybe the next pointer. But if you have more pointers, then you can accommodate any number of nodes. Remember, data structures are adjustable. You are the designers, and so you can come up with different ways to get the job done. Other ideas for how we can represent graphs in code? Mm-hmm. Say the last part again.
Graph A, B,
Mm-hmm.
score.
So, yeah, something like that. Okay. Other ideas? Okay, so these are really good ideas. I'm going to talk about two implementations that have become pretty much standard. And so one of them is what we call an adjacency matrix, and the other one we call an adjacency list. And so I feel like, so this is the graph. We've got 1, 2, 3, 4, 5 vertices, and then different colored edges between them. And first off, the adjacency matrix is basically just a two-dimensional array where we've got labels 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. We wanted to start at 0 and count that way, we could. It's just a matter of labeling the vertices. And we say that if there's no edge from X to Y, then we put 0 in that row and column. If there is an edge, then we put a 1. So let's see, 1 is adjacent to 2. So 1 is adjacent to 2 here. So we've got a 1. 1 is also adjacent to 5. So we put a 1 in that column as well, and so on. So that's this adjacency matrix, because this is a matrix. The other representation is adjacency list, which combines something like an array and linked list, where we've got the same idea, where we've got an array for here are our vertices 1, 2, 3, 4, 5, and then we start a linked list of 1 points to 2 and 5, 2 points to 1, 3, 4, and 5, or 1, 5, 4, and 3. Order doesn't particularly matter, although it might if we wanted to sort that. 3 is adjacent to 2 and 4. 4 is adjacent to 2, 3, and 5. And 5 is adjacent to 1, 2, and 4. So another way to represent that. If it's weighted, then maybe we, like if the weight between 5 and 4 was 3, maybe we put a 3 there instead of a 1. For the adjacency list, if we wanted to accommodate weight or anything else, I would say since we're using a linked list, just define the node class however we want to. So maybe our node class includes the weight. Just tack that on. Any questions about how we represent this? I will say another easy way to represent the graph. When we go back here, one of the ways that I first think of is if you're like working in Python, kind of like the hash table is to use like a dictionary. Where, and with a dictionary, you can come up with something like the adjacency list, where if you have the key be the name of the vertex, then you can have, so let's say, a list of here are all the vertices that this one's adjacent to. So this is one of the things that you, as in the video, are gonna, if you're the programmer, are gonna think of how can I represent this without using any library. So step 1 in the video is to do this without using a library, only built-in data structures. And then step 2 is to install a graph library and use that. and practice using the algorithm there. In terms of which one is better, the matrix or the list. So adjacency matrices win to check if something's in a graph because matrices have order 1 lookup. But pretty much anything else, instead of edge insertion or deletion and then memory on dense graphs meaning like a lot of vertices and edges, sparse graphs meaning not that many, like your typical dense and sparse definitions. In pretty much any other case, adjacency list wins. But again, it's preference and also how big is your graph. So I've got this list for when you want to reference for your video of what library you want to use. A lot of these are Python because Python's pretty much the most popular language, at least among people at this school. So yeah, so you can have maybe a hash map or a dictionary or a two-dimensional array. Network X or networks is a popular one, but that one gets slower for large graphs. Alternatives include GraphTool, SciPy, which I've worked with a bit, iGraph, which also has something for R. Wikipedia says that there is Microsoft Automatic Graph Layout. So if you've got a Windows computer and want to try that out, and let me know how it goes. GraphViz is kind of a visualization tool that is used on a lot of different systems. And then there's also for C++, there's the Boost graph library, which whenever I have tried to install Boost graph library on a machine, it has failed miserably. But that's also just because I get weird errors on stuff all the time. So you may have better luck. But there's a lot of options for you to implement graphs and to use a library. So part of the video assignment is choose a library either from this list, or if you do some Googling, choose another that sounds good to you. And you've got data, put your data into a graph in the library format. And then chances are they're going to have the algorithm that you need. So just call that, run it, and show the output. Any questions so far? Okay, so now let's look at some interesting problems. The first of which is traversal. We've done this with trees already. Remember, so like if we have a binary tree, we looked at how do we go around the tree to list every node. So we go around the tree kind of like that. We want to do the same things, but for graphs. And so graphs may have some cycles, which means that our traversal methods for trees are probably not going to work. And so there are two very common traversal algorithms that you as a programmer should know. So the idea is we're going to go through all of the vertices. And the way that the book describes it, each vertex has one of 3 statuses. In the videos that I've picked out, it just has 2, which is visited and unvisited. So pick and choose which one makes sense to your brain better. But the idea is we have either gotten there and done all the things we need to do, or we haven't. And so the book breaks it down to either we haven't gotten there yet, or either we've gotten there but haven't done all the things we need to do, or we've gotten there and we've done all the things, this one's done. You can think about it if you're like navigating a labyrinth or a maze, and if you're keeping notes as you go of trying to keep track of every possible offshoot. Your traversal is we're just exploring this and trying to write down, like make a map of this labyrinth. And so it's different ways of we're starting here and we're going to discover all of it through this process. It's just different ways to approach it. Okay, and this is basically what I just said. So undiscovered is we haven't gotten there yet. Discovered is we've gotten there but haven't gone through all the possibilities. Processed means we did everything, we're done here. Let's move on to the next one. Okay, so we're gonna go through two main algorithms. One, breadth first search, and the other is depth first search. And so breadth first is abbreviated BFS, and then depth first is DFS. The result from our algorithm is going to generally be some list of nodes. So like 1, 2, 5, 7, 3, 4 for this one. So kind of like when you do a tree traversal and you list all of the nodes, that's again something like what we're going to get. We're also going to get a spanning tree. So as we go through the graph, we're going to record, here are the edges that I took in order to discover this node. And as we do that, once we're done, we'll get a spanning tree, which is the tree where every vertex of the original graph is included. And so, like, for this one, the one on the top is the bolder black lines. So like 1 to 2, 1 to 5, 1 to 7, 2 to 3, and 2 to 4. That's my spanning tree, the graph by the red edges. And then also 5 to 6. And then the ones that aren't red at the moment are just not included. Yeah, question? Oh, no question. Okay, so we're gonna get a spanning tree at the result of this. We may also get back edges as you go. So this is something that you'll see in DFS, where as you go through the graph, sometimes you have to jump back. And so back edges are going to be included, which typically when you draw them, it shows up as like a different color. Okay, so for each of these, I've got videos here. We're going to watch the videos for at least BFS and DFS. Also to kind of give you an example for the video. The main idea before we get there is it's got this sort of like the radio signal I like, where we are going to, if we've got, actually, let me do this. So we go through the different levels to start with. So this is breadth first, where if we start like at 1, then we look at all of 1's neighbors, and then we go through each of those, and then we look at all of their neighbors. So we go through 1 level at a time. The way we're going to do that, we're going to use a queue. And so we start somewhere, we add that vertex to the queue, and then until we know that the whole graph is processed, we're going to dequeue it. So mark that we've processed it, and then enqueue all of its neighbors, and then keep going until we've gone through the whole graph. Okay, I'll stop recording while we watch the video. All right, so that's BFS. I'll pull up the pseudocode from the video while you do this. I just also wanted to mention that the book has pseudocode, which is a fair bit more complicated than the one the video shows, because they've got 3 different statuses. Or so the video has 2 statuses, the book has 3. But if you read through this pseudocode, it's doing basically the same thing. It just maybe adds a little bit more work to the step. So once you understand the basic idea of the algorithm, then you can, if you want to formalize it a little bit more, you can and get something like this. Otherwise, you can go simpler. I will say that so you know how in the video when, so let's take, if we have A, B, C, and D. So the idea was that we NQA and then we DQ it, and then NQ all of its children, all of its neighbors. This kind of gray area status of what are we doing with A right now, that's what the difference between discovered and processed in the book is. So when we're not done with A, we still have to add all of its neighbors to the queue. Then A is discovered but not processed because we haven't added all of its neighbors. So I will remark that that seems to be the main difference. Okay, so I've got packets for you. Let me pull that up on here. And maybe go all the way up to the top. Okay, so the structure of the packet, I've got 2 pages for you that are roughly the same. So I've got a series of 1, 2, 3, 4, 5 graphs for you to practice with BFS and DFS. And then since we're going through other algorithms, I've replicated the graphs for the other ones that we'll look through, just so that it doesn't get too crowded. So what I would like you to do for the next, I don't know, 5-10 minutes is work through BFS on the graphs that have been provided. You could start, so there's options, right? We could start, since we're not working with trees, there's options for where we start. We could start with A, we could start with F. So talk with your neighbors, make a decision. Where do you want to start? Maybe start with A for the first one and start with something else for the next ones. And go through the process of the algorithms. And I would like to know what are the, so what's the order in which you process things? So like when you DQ something, then that would be you're reporting it. So first of all, I want to know your list. And second of all, I want you to draw, maybe if you have different colors or like a straight line versus a squiggly line, draw on the graph of what's the tree edges that you took. And so the tree, so for this one, as we go through this process with DFS, if we start at 1, when we look at 2, we NQ 3 and 4. And then when we get to 5, since 4 is already in the queue, we don't NQ it. And so that's why this edge between 5 and 4 isn't included. Okay, take a stab at it and let me know if you have any questions. Okay, let's use purple and look at this one specifically. Okay, so let's say I start at C, just so we don't start at A. So I've got my Q here, and I NQ C, and then I can DQ it, write it down, and then add its neighbors. So B and D. I could go D and B if I wanted to, or I could say alphabetical order wins and NQ. That's not how you spell D. Or I can say B and D. That's a choice that I make. So once I have DQ'd C, I've added B and D. There's two edges of my tree. And then I DQ the next thing in the queue, which is B. So I write down B and then I add its neighbors. B's neighbors include C, which we've already done, so I'm not going to bother with it, and A. We haven't done anything with A, so let's add it. Okay, now B is done. Next is D. And then we add any of D's neighbors, which are C and A, both of it which are already done. And then we've got A. Okay, we've done one half of this graph, which we call a component, but it's still got vertices and edges that we haven't processed yet. So what we do is we just pick another vertex of what's left and keep going. So say we pick F. We add F, then DQ it, add its neighbors, E and G. And then we continue the process. So E, its neighbor is H. And then G, all its neighbors are covered. And then H. And so now we have found the BFS algorithm for this whole graph, but has two separate components. And we know that it has two components because we reached an empty queue in the middle of it. So that's something useful to know. But the way that we write it is just one long line of letters because it's all one graph. Any questions on this one? There's a similar process for this one. Like if you start at 1, then it's easy. But if you don't start at 1, then it's hard. And then you'll probably have to do a lot of, restart, go, restart, go. In 485, we talked about this today. There's this notion of a graph being connected, which means you can get from one vertex to any other vertex. And for directed graphs, which is what this is because there's arrows, there's a notion of strongly connected, which is with the graph that has arrows, can you get from one vertex to any other vertex? And if we do BFS with starting somewhere other than 1, we see that the answer is no. And so this analogy is, say you've got like one-way streets in your town. You want to be able to get from one place to any other place in the town. You don't want to have to like, oh, I'm going to go onto a one-way street. Oh, no, this is bad. So you want your town to be strongly connected. And so doing BFS on like 3 is going to show you probably, no, this is not strongly connected. Strongly connected. Let's see if I can think on the spot. So for this one, if we start over here, we can get to the other three. So we can't go this way, but we could go around and get there. And so on we could do that for the other vertices as well. So we don't care, like, is it direct? We just care, like, is there a path from one to the other? Okay, we've got 10 minutes. Let me see. So the applications of BFS, I'm just going to kind of hand wave over it. As we've seen, it helps us find connected components, which are these connected parts of the graph. That's useful for all sorts of applications. It can also help if we tweak the BFS algorithm. It helps us do something called coloring. We're going back to kindergarten again, where we're doing like connect the dots and coloring. But coloring is where we like assign a vertex a color. And these help us do like scheduling algorithms. So you can see of like, if in this graph, maybe the vertices are classes and the edges they happen at the same time, then we can color it and see that, oh, the blue classes could all happen at the same time, or something like that, where they can help you find these three things can happen together, these three things can happen together, and so on, which is useful for scheduling. If you look into compilers, this also helps for register allocation. And Wikipedia also says Sudoku puzzles. So I challenge you to pull up maybe an easy Sudoku puzzle and try and see how that applies. Okay, I don't know that I have, I don't know that I have enough time that I want to do DFS today. Okay, so next time we'll start with DFS. We'll do the examples. And then we'll start looking at weighted graphs. Thank you for coming. I will see you on Thursday. Please give me your packets, your divide and conquer packets, and or your homework for divide and conquer.